Okay, so what I have here is the exam that we gave during the summer semester of 2016, which was just the summer before last. The reason I'm not doing the exam from fall of 2016 is because I will post that on Canvas as a practice exam for you to work through on your own. I will also provide you with the solutions to it. First off, you want to make sure and put your name at the top of your file here so that in case it gets lost, I know who it belongs to. It should not be a problem. So first and foremost, make sure you go through the exam real quickly and just look to see if there's really easy problems that you can get done real quick. I hate for you to lose points on an easy problem because you got stuck on a hard one. Unless the problem, problem 2 works on problem 1, then you really don't need to work them in order. So I'm just going to start here with problem 1. Okay, so it says create a vector named x1 from 1000 to 2000 with an increment of 200. So the easiest way to do that is just go with the colon operator here with the beginning point, the incrementation, and the final number. So that will create a vector from 1000 to 2000 in the increments of 200. Spaces shouldn't make a difference. Okay. Oh, I gotta get rid of this. I can't see. So here is my solutions to first part A. So part B tells us to create a vector named x2 from minus pi to pi with an increment of pi over 10. And then again, we can go minus pi to pi divided by 10 to pi. Okay. Part C, create a linearly, that word right there, spaced vector named x3 from minus 6.5 to pi with 5 values. Okay, so x3, because it's linearly, why can't I say that word? I don't know. Linearly spaced, we're going to use the line space command, which is, if you put an N in there, is just short for linear spacing. And then this one takes 3 inputs: your beginning value separated by a comma, your ending value separated by a comma, and how many numbers you want in the vector. And beep beep, somebody just joined us. Hi, welcome. We are working problem the exam from 2016 summer. So I just got started. This is all you've missed so far. I've made 3 vectors. Okay, part D here is a logarithmically spaced vector from 100 to, looks like 100,000 with 4 values. So x, it doesn't tell us, but we're going to do x4. Okay, using the log space, you need to have 3 inputs, but this is going to be the log of the values in which, and if you put space in there, it works better. The log of the values that you want. So 100 is log 2. 100,000 is log, how many zeros? That looks like about 5. Okay, and then we want 4 values. So now if we run this, what? That's not a I1, that's an I. Okay, so here we see, and if you are more good at math than I am, you'll see that this is spaced by pi over 10, 3.14, so that's about right. So this is from -6 to pi with 5 values, and this is logarithmically spaced from 100 to 100,000 with 4 values. So that was problem 1. Okay. Now we'll move on to problem number 2. Newton's law of universal gravitation tells us that the force exerted by one particle on another is F equals gm, mass of one object times mass of the second object divided by the square of the distance between them. Not intended to be math lab code. The universal gravitational constant G is a huge number with lots of units. Find the force exerted by the Earth on the Sun if the mass of the Earth is 6 times 10 to the 24 kilograms and the mass of the Sun is a whole bunch of kilograms. For values of R from 150 E9 meters, which is the average distance between the Earth and the Sun, to a bunch more meters, from the Sun to Pluto. Be sure to define appropriate spacing for this vector. Yeah, okay, because if we're going from 1E9 to, this is basically 7E10, if you go by 1, that's going to be a lot of digits. Okay, so first off, we need to define the mass of the Earth, which was 6E24, and that's going to be in kilograms. And I personally like to put my units over here so that I know what I'm dealing with. Okay, and then the mass of the Sun is equal to 1.9891 E30. Let's give us a little more room. In kilograms. Okay, and then we're going to cheat to do G. G is equal to, not the minus sign, this number right here. We're just going to come, and we're going to grab the units too, just so we have them. Okay, so this is in Newton meter kilograms squared. So we got our kilograms and our meters. So this will leave us an answer in newtons, assuming we have meters, okay, in our length. Okay, so now we're going to define our R value. R is going to go from 150 E9, and let's go let's start with 100 E9 and see what kind of a thing we get from that. And we're going to go to 7375 E9s. And we still need more space. And this is going to be meters. Okay, so this formatting here is not required for your exam. This is just my OCD. So our force then is going to be equal to G times mass of the Earth times the mass of the Sun, and that's going to be divided by R, and because it's a vector we need to raise it to the 2 and we need to make it a lowercase r. Okay, and we want to show that to the screen. Okay, however, because this is also a vector, we need to dot divide to make it divide, because you can't divide by a vector, it's not possible. So there's our values, and we got 72 of them, 73. Let's go by 300, cut that down so that we can see it. Okay, if we were plotting, we would want more data points in here, but because it's just showing to the screen, it doesn't say to make a chart, does it? A table will be for spacing for this vector. It just says find the force exerted on it. Okay, so that's problem number 2. Problem number 3. Using data from problem 2. Oh, now it does want us to plot. Haha. Okay, so We're going to suppress X. We don't want it going to the screen. And we're going to make this a lot more data points so we get a smooth plot. Using the data from problem 2, plot the R value on the x-axis and the force on the y-axis. So this is going to be a plot. On the x-axis is our R value, and on the y-axis is our F value. The table, you may need to increase the number of points plotted in number 2 to get a good graph. Okay, I did. And then it wants to do a title. May the force be with you. Ha ha ha, he's an idiot. Oh, thank you. Y label is going to be force, and that's in newtons. And the X label is distance, and that's in meters. And a grid, okay. And then we'll turn the grid on. And we'll plot, and there's our plot. Yeah. Okay. Holler if I'm going too fast for you. I'm just cruising along here. Okay, problem number 4. Use the subplot command to create the following 4 graphs in the same figure. Okay, so this is clear. So, first off, x from 0 to 10 for all of them. So we'll just define x up here, x equals 0, and we're going to do a nice smooth line, 10, and do that. Okay, so for the first plot, y equals the sine of x. Suppress the output. Okay, so subplots. Call up the subplot command, and we'll do a 2 by 2, so 2 rows, 2 columns, and this will be the first plot. And rectangular, so it's just going to be a regular plot. And we want x, y, and does it want? Don't forget title. Okay, so it's a rectangular plot. Well, not rectangular, coordinate system, you idiot. I get tired of you calling me that. Okay, and so the next one is going to be y equals exp of x. And we're going to cheat here and copy this down. And this will be the second plot. And this is going to be plot log x.
Oh, I'm so tired. I want to go home. I don't know what I'm doing.
Okay, so a log, a brief moment of insanity. So this is a semi-log x, and that's going to be of our x and our y values, and we'll do a title here. Semi-log x plot. Okay, and then plot of, okay, so here we're going to have now y is equal to x dot raised to the deuce plus 3, suppress the output. It's going to be a semi-log y, so we're going to cheat and copy all that down here and just change that to a y and that to a y. And then for the last one, y is equal to 5 dot raised to the x. Oh, wait a minute, we gotta come up here and change that, otherwise it's gonna go right. We want that in the third plot. And put this one in the last spot, and this is going to be a log plot. And cross our fingers and hope it works. Yeah, poof, there we go. So there's our neat little plot. So this is the rectangular coordinates, semi-log x, semi-log y, and a log. Okay. Okay. The writing is very small and you cannot tell. Oh, dang. I know there's a way to change the size of the font here, and off the top of my head, I'm not sure where that's at. I am recording this, so you can pull up the video, and hopefully it'll be better to see, and I'll work on figuring out how to get the text larger for the next go round. My apologies. Why do I have I don't want that on there. Okay, problem number 5. Create a table with the integers of 1 through 10 in column 1, log base 2 of the integers in column 2, and the corresponding natural log in column 3, and log 10 in column 4. Okay, so we're going to start with our x value. Now you can do this in a couple of different ways. One, you can define all of the values for each column. So y1 would be equal to what am I doing here? Log 2 of each number in column 2. Log 2, so I'm going to do log of x divided by log 2. That'll change the base. Y2 would be the natural log of x. Oh, let's suppress these outputs. No, not there, down here. Y3 is going to be log base 10 of x. And then, there's several ways to do your table. There is a table function. I personally don't like using it, but I don't mark you wrong if you do. Besides that, I usually override it by using table as a variable. You're an idiot. Oh, thank you. So these are going to be currently row vectors, so I'm going to change them to column vectors. And I'm hoping that's right. I guess we'll find out when I create my vector and look at it. And Y3, close it, and execute. What? Don't tell me that. Oh, because you got to transpose all of them, you idiot. There we go. And in a future chapter coming up for the next section, you'll learn how to use the display command to put headers and this is not required for the exam. This is just me showing off. You're an idiot. Oh, thank you. F print F, and then we're going to have, let's see, there's two values, so 2.0F with the percent sign in the front, followed by a percent, and what do we got? Let's do 3 places, so that would be 5.3 F, and percent 5.3 F, and 5.3 F, and comma, and table, and we need to hit the L button to begin with and transpose that. And we're going to need a little more spacing in here. Oh, you forgot the one little minor important thing you got to do in a return line. And you'll learn that in another, and if you put a percent sign on here, it prints off better too. There we go. We'll learn that in another chapter, so I don't expect you to do that on the exam. Is if you get to this point right here, that's all it would be required to receive full credit for that problem. Okay, here we go. The value of the trigonometric function can be estimated by using a Maclaurin series. For example, cosine x is approximately 1 minus x squared over 2 factorial plus x fourth over 4 factorial minus yada yada. Recall that the mathematical symbol for factorial is the exclamation point, but MATLAB uses built-in factorial function, and therefore the series can be expressed as 1 dot dot dot. Where'd all the dots go? Did that get erased? I don't know. So, write an anonymous function called myCosine to find the value of cosine using the first 4 terms in the series as shown above. Test your function by using cosine 1 with both the built-in function and with your anonymous function. Okay, now remember, with anonymous, that's not an E, that's an A. With anonymous functions, those go right inside of your main script file. They do not require to be in a separate M file like a regular user-defined function. User-defined functions have to be in their own M file. So we're going to create an anonymous function called myCosine, and to do that we begin by putting a @ symbol, and then the variable that's going to be within the function, and then the equation. So that's 1 minus x raised to the deuce divided by 2 factorial. Well, 2 factorial is 1 times 2, right? So we can just go 2. And then we got to do plus x raised to the 4th divided by factorial of 4 minus x raised to the 6th divided by factorial 6. And there's our first 4 terms. There's 1, 2, 3, 4 terms. And we'll suppress that. And then now we'll call up our anonymous function, test it with 1, and then we will also test it with the built-in MATLAB function of cosine, and those both should come out nearly the same. And they do. 4.3 and 4. Maybe if we change the format so that it's a little bit longer, it might show, see, if we go a little bit longer, now you start seeing a difference in the two, because this one needs to go out further to get more accurate. But with 4 places, it's pretty accurate within significant figures. Okay. So that was anonymous functions. Now it wants us to, on problem 7, create a user-defined function called express, representing the following expression. Not necessarily. Okay, so what I like to do when I'm doing user-defined functions, especially in exam, is I'll copy that. I'll come up here and create this, and very first line needs to be a function, followed by your output variables, the name of your function with your input variables. And I hope I got that right. Express, represented, and we're bringing in an S. Okay, so I copy this in here so that I can see exactly what I'm doing. That way I don't have to go back and forth between the exam and my function to see what I'm supposed to be doing. So this is a really simple, straightforward function. You got one variable in, one variable out, and a very simple equation. So we'll just assign the value of our equation, which is going to be, if the equal sign works better, equals 5 plus the sine of x plus 2 times the cosine of x. And if you don't suppress the output in your function, it will show up in here not only as you run the function, but if you down here, so your display will be shown twice. So I always like to and put a suppress in my functions. You can finish this off with an and. It's completely optional. It'll work without or with. Now you'll notice that as you do a save, it automatically defaults to the name of your function. File name became as an express. There's already one there. So this is the solution that I provided last semester. So I'm going to change the name of that one so that it's, and we'll save that. So now that when we go to our current folder, this is the file I just wrote, and this was the one from last, 2 semesters ago. Okay, so there's my user-defined function. Now we'll go back to here, and we'll just put in a note here, say C function. Okay, so B, evaluate your function for x equals 3. So to evaluate our user-defined functions, you just use it like you would any other MATLAB function. You just call it up and give it its input. And we should see a value. Oh, and I got to get that back to the short format. I don't like all those digits. I'm guessing that's the right value. Let's see. Let's do cosine of. Let's calculate it. It should be right. 5 plus sine of 3 plus 2 times cosine of 3. Oh, and we left the 5 off. There we go. Same values. So our math works. Okay. So that's a user-defined function. This one was fairly simple and straightforward. Okay, this one here, some students struggled with, and that really hurts because this is a problem that I wrote. This is dealing with stuff that I do during my full-time job. I deal with pipeline inspection tools that inspect oil and gas pipe, and actually mortar-lined aqueduct lines too. So oil and gas steel pipelines are inspected on a regular basis, looking for areas of reduced cross-sectional area in the wall thickness. One of the technologies used to inspect these pipelines is called magnetic flux leakage, or intelligent pigging. These tools induce a magnetic field into the pipe and then pass sensors by looking for changes in the background magnetic field. If anybody's interested in more information on that, just contact me. I'll bore you for a few minutes. So part 1, load the defects.txt file using the load command. Okay, and this one is very important to use because let's go ahead and do that. We're going to load, what was it called? Defects. dot text, and we're going to go ahead and load that in right now. As you can see, okay, oh, it's a small file. There's only 433 rows and 6 columns. So that's an awful long, big file. If you were to copy and paste the data in here, it makes it really hard to grade. So the first column is a time. Columns 2 through 5 are background readings from the sensors recorded in counts. This is just some general knowledge. Okay, so create a vector called time by extracting column 1 from the defect data. Okay, so we're going to get time, and we're going to extract defects, and we want the first column, so we want all the rows from the first column. There's part B. Part C, create a vector called data by extracting column 5 from the defect data file. So we're going to go back to defects, and we're going to extract all the rows from the 5th column and suppress that output. And then we're going to plot these two vectors, make the line dotted, and include titles and labels. Oh no, somebody turned off my... I just turned off the heat. Hang on, my feet are getting cold. Don't laugh at me, that hurts. Okay, so we're going to plot these two data points. So we're going to put our time on the x-axis and our data on the y-axis, and we're going to make them dotted by doing the colon in between 2 single quotation marks. So we're going to include a title, and we'll just call this defect data, and labels. The Y label is going to be called that's actually MFL signal in counts. I like to put units on everything because when I was a student in community college, I got in the habit not doing units, and when I transferred up to the University of Utah in my very first lab, I didn't do the units. Boy, I lost a lot of points in that lab. So I learned very quickly to do units on just about everything. One of those is wrong. Yeah, that's what I thought. It's the first one. See, I'm tired. I can't even spell my name right. So the X label is going to be time, and it was a made-up file, so we'll just say that it's in seconds. Okay, so it's really hard to see what's going on with this, but this point right here, and this is just background, this has nothing to do with the exam. This point right here and this point right here are the defects in the pipe. Well, it wasn't a pipe, it was a test bar that I was running for some R&D work. But those are where the defects are. This here is background. And since I've done this, I have learned how to see that this should be a straight line going across here for background, but because of my setup, it didn't, but I've learned how to fix that so that it does do it more gooder now. Anyway, that's not part of the test. So that was pretty straightforward. Loading the data file, extracting two vectors out of it, and plotting it. Okay. Problem number 9. We're 34 minutes into this exam. So there are 3 natural isotopes of carbon, C12, C13, C14. The atomic weight reported on periodic tables is a weighted average of the masses of these isotopes based on their relative abundance. We use the dot product. Have we learned the dot product? I think we have learned. To find the appropriate approximate average atomic weight of carbon from the following data. Okay, I question that because a couple of semesters ago I did the first exam and I ended up putting questions on the first exam with material from the second exam, and the students looked at that and said, "What? We don't know how to do this." Sorry. Okay, so, but I didn't write this exam, so. But I have looked at it, and it's not that it should be probably too easy. Okay, so I'm going to create me a vector here with the data from the chart, 0033 and 14.0032, and the relative abundance is equal to a square bracket, a point, a 9, a 8, a 9, and a 3, and a point, a 1, a 0, no, I'm going to have a 0 there first, then a 106, and then 3 zeros and a 1. And suppress the output, and then we'll just dot those two together. Oops, capitalize them, they'll work better. And output, and there's your approximate average atomic weight. Okay, so last problem here is your system of linear equations. Use matrix math to solve the following. Okay, and now I'll tell you now, I know there are several ways to solve system of linear equations in MATLAB, but if the problem tells you to use the inverse process and the left division, if you don't do both, you won't get full credit for it. So first thing we do is we establish our A matrix, which is going to be a 6. Let's see, we got X, Y, Z. Okay, 6, 6, and a 1. And I like to build my matrices so they look like a matrix. 2, and another 2, and we don't need this, but I'll put it in anyway. Not a 2. And then a 1, and a 1, and a 1. And a closing bracket, and a close thingy there. And then our R value vector is going to be the 0, 15, and a 10. Okay, so using the inverse method is going to be B is equal to, I probably got those letters backwards, but it's not important. So we're going to do the inverse of A times R. And then the left divide. Oh, let's do that. Yeah. Make it somewhat meaningful so we can see the results out. And then if we do left, come on, you can do it. Left divide is just a matter of A and the left divide sign and an R. And those two should come out with the same values. -5, 3, and 12. And that's it. That was the exam for the summer semester of 2016. Any questions? I know I went through that kind of quickly. Took me 38 minutes.
Is that last question covered in chapter 6?
The system of linear equations. This may be the exam that I was thinking of that I wrote that had problems from a different chapter. It might be that the system of linear equations may come from chapters from a future chapter. I can guarantee you now that there are no linear equations on the exam that you'll be taking next week. But let me just check here real quick and see where. It's just when you're doing these tests for 100 years, you kind of forget what chapters are covered and what, and you just. There we go. Equations. I'm guessing that 371 is going to be in a future chapter. Yeah, that's going to be covered in the next section of materials. So, you won't see a problem 10 on the exam. So, forget this one existed. It's gone.
Cool.